Good morning, sir. This is 15 BCL 1082 and I am here to present my assignment on fluid mechanics, the second assignment, and my topic is open channel flow and hydraulic jump. So let me give you an introduction about hydraulic jump. Hydraulic jump is basically when there is any obstruction in the flow of water, or generally we take the fluid as water. When there is any obstruction in the flow of liquid, there is a sharp change from supercritical to subcritical. This sharp change is called hydraulic jump. Hydraulic jump is technically defined as the rise of water level which takes place due to the transformation of unstable shooting to the stable streaming flow, which is subcritical. When hydraulic jump takes place, a lot of energy due to eddy formation and turbulence occurs. Hydraulic jump, we can also find the depth of the hydraulic jump. Now let me tell you a bit about flow in open channels. A basic introduction for flow in open channels is defined as the flow of liquid with free surface, a surface which has constant atmospheric pressure such as water. Thus, a liquid flowing at the atmospheric pressure through a passage under is known as flow over open channels. There are many different types of classification for the open channel flow. The four types are: steady flow and unsteady flow. If the flow characteristics such as depth, velocity, rate of flow at any point in the open channel do not change with respect to time, then it is called steady flow. If, however, the flow characteristics at any point do not change, the flow characteristics such as depth, velocity of flow at any point in the open channel do change with respect to the time, then it is called steady flow. The other different types of classification are also known as uniform flow. Uniform flow and non-uniform flow. If for a given length of channel, the velocity of flow, depth, slope and cross-section remains constant, the flow is said to be uniform in nature. If for the given length of channel, the velocity of the flow, depth, slope and cross-section do not remain constant, the flow is said to be non-uniform in nature. The other different types of classification in open channel flow are rapidly varying flow and gradually varying flow. Rapidly varying flow is defined as that flow in which depth of flow changes abruptly over a small length of channel. That is, when there is a small obstruction in the path of water, thus depth of flow changes rapidly over a short length of channel. The other type, gradually varying flow, is defined as that flow in which flow of water changes gradually over a long length of channel. Thus, length of flow change rapidly over a long length of channel is called gradually varying flow. The main difference between these two flows is that rapidly varying flow occurs for short channel length and gradually varying flow occurs for long channel length. Now let us go on to the last type of classification. That is laminar flow and turbulent flow. Before we try to understand what laminar and turbulent flow is, let us understand what Reynolds number is. Reynolds number is defined as rho into velocity into hydraulic depth divided by viscosity. So over here, if the laminar flow, the flow in open channels is said to be laminar only if the Reynolds number is less than 500 or 600. Reynolds number in case of open channels is the same rho into V into R divided by mu. This rho into V into R divided by mu can also be expressed in terms of its kinetic viscosity. Over here, R is the mean velocity, which is R is the hydraulic radius, that is the cross-sectional area of the flow normal to the direction divided by its Vetter per meter. The turbulent flow is said to be that type of flow that occurs if the Reynolds number is greater than 2300, and this type of flow occurs only in very rough patches. So over here also the units have their usual meanings. Let us go on to the next type of flow, that is subcritical, critical and supercritical flow. This type of flow makes do because of the different Freud number that could occur with each flow. The subcritical flow Freud number, if it is less than 1, the flow is said to be subcritical. The Freud number, as we know, is V divided by root of G into R, where V is the velocity and G is the gravity and R is the hydraulic depth. If the Freud number, however, is greater than 1, then this flow is called supercritical flow. When the Freud number is equal to 1, then this flow is called critical flow. This flow is useful for, this classification is generally useful for hydraulic jump. Let us now go on to the most economical section of each. Let us now go on to the most economical section of each type of channel flow. There are 3 sections. There are 2 sections that I am going to talk about, and usually we use rectangular, triangular and trapezium. The most economical section will occur when the perimeter of the section is minimum. Thus, we find the perimeter of each section and we equate it to 0. And when we equate it to 0, we find the perimeter, which means not just the whole perimeter but only the wetted perimeter of the section. There are 3 types of shapes that are usually used: rectangle, triangle and trapezium. However, here we are only going to discuss about the rectangle, the triangle, the rectangle and the trapezium derivation. Now let me tell you about the hydraulic depth of different types of shapes such as liquid flow and circular, sector, etc. Here it is. Here, as you can see, we find the area of the sector, which is equal to, of the circular sector, which is r square into theta minus sine theta cos theta. The perimeter is 2 into r theta. And finally, the hydraulic depth is obtained by getting the area divided, the wetted area divided by the perimeter, which is theta minus sine theta cos theta by 2 theta into r. And that is for the circular channel. For trapezoidal channel, the area is y into b plus y and the perimeter is b plus 2y. So dividing this, we get the hydraulic radius. For a liquid film of thickness y, the hydraulic depth is equal to yb divided by b plus 2y. So cancelling, we get yb by b, which is equal to b, and this y is the hydraulic depth for a liquid film of thickness. Now let us go on to the derivation for finding the most economic section of a rectangle. The hydraulic depth of a rectangle is bh by b plus 2h, and the hydraulic depth for a trapezoidal is b plus mh into h divided by b plus 2h into root of 1 plus m cube, and the hydraulic depth for a triangle is mh divided by 2 into root of 1 plus m square. The derivation for the most economic rectangular channel is first we have to find the area, which is equal to b into d, then the perimeter, which is equal to b plus 2d. Then we know that the breadth is equal to area divided by depth. So in the equation perimeter equal to b plus 2d, we substitute this. We get p equal to a by d plus 2d. Deriving a with respect to d, we get a by d square plus 2 equal to 0. Then a equal to 2d square, and we know that a is equal to bd. So we get finally get b equal to 2d. M as the hydraulic radius we have to find. So we get hydraulic radius as equal to area divided by perimeter. So b into d divided by b plus 2d. Substituting this b equal to 2d, we get m equal to d by 2. The talking points that I want to highlight over here. is that for a rectangular section to be most economical, we need breadth to be equal to twice the times of depth and hydraulic depth to be twice as big as the depth. So now let us go on to derivation for the most economic trapezoidal channels. Here I would like you to take a very close look at the figure. The figure over here, we take this as n into d and this as d. We know that this will be proportionate to this, so the sloping side will be equal to d square plus nd square. D into root of n square plus 1 will be the sloping side. This is very important as we are about to use its area. Area of flow is equal to BC plus AD by 2 into D equal to B plus ND into ND, and area by diameter is equal to B plus ND. Perimeter equal to AB plus BC plus CD. We do not take the top area. Into is equal to finally B plus 2D into root of n square plus 1. Perimeter is equal to A by D minus ND plus 2D into root of n square plus 1. Differentiating the above equation with respect to D and equating it to 0, we get A by D square plus n equal to 2 into root of n square plus 1. Substituting A, we get B plus ND into D by D square plus n equal to 2 into root of n square plus 1. Finally, we get B plus 2ND by 2 equal to D square root of n square plus 1, which is nothing more than half of the top width. D into root of n square plus 1 is equal to one of the sloping sides. We also have to find out the hydraulic depth, which is equal to area by perimeter. Hydraulic depth is equal to B plus ND into D by 2 into B plus ND, which is equal to D by 2. Hence, the conditions for the most economic section of the trapezoidal channel are B plus 2 ND by 2 equal to D into root of n square plus 1, M equal to D by 2. Now let me talk to you about the next topic, hydraulic jump. Let me give you a clear picture of what hydraulic jump looks like. The hydraulic jump occurs over here. As you can see, the hydraulic jump occurs over here, and it is due to the abrupt change in flow that has occurred. Hydraulic jump is defined as the rise of water level which takes place due to the transformation of the unstable shooting flow to the stable streaming flow, which is subcritical flow. When hydraulic jump takes place, a loss of energy due to eddy formation occurs. Now let us try to do the derivation for the depth of the hydraulic jump. The following assumptions are made. Flow is uniform and pressure distribution is due to the hydrostatic force before and after the jump. Losses due to friction on the surface of the bed of the channel are small and hence neglected. The slope of the bed of the channel is small, so that the component of weight of the fluid in the direction of the flow is small. Next we equate. Pressure force before the jump is equal to rho into G into A into I, where A is the area D1 into 1 and I is equal to D1 by 2. This goes the same for pressure force after jump. According to the rate of change of momentum principle, there is a net force which incurs a rate of change of moment, which is rho into Q into velocity equal to rho into G into D2 square minus D1 square. So, equating both the equations and solving, we will get V1 equal to Q1 by D1 equal to and V2 equal to Q2 by D2. We have to substitute these both of this in the equation. D square plus D1 D2 minus 2Q square by GD1. Its root will be D2 equal to minus D1 plus root of D square minus 4 into 1 minus 2Q square by GD1 by 2 square 1. Thus, this is the depth of the hydraulic jump. Now, let me tell you about the expression for the loss of energy due to the hydraulic jump. Here we substitute q square equal to g into d1 into d2 into d2 plus d1 by 2. H we know we will get as d2 minus d1 raised to 3 divided by 4 d1 d square, which is the formula for the expression of loss of energy due to hydraulic jump. That is all I will be taking for today. Thank you, sir.